Graphing systems notes. Objective, to solve systems of linear equations by graphing. The graphing method. So we've written the equations, now we're going to start graphing them. Graph all equations on the same grid and determine the ordered pair for the point of intersection. So what we're doing now is we're going to graph two lines and see where they intersect. Okay, this is the point where the lines cross each other. So we're going to have 2 points and find out where they cross. The solution, okay. The solution to a system of linear equations is an ordered pair x comma y that represents the point in which these systems of equations will intersect, cross, or be the same. And I say be the same because be the same is when you're looking at a table. You don't necessarily actually have the graph going on. You're going to have the table to look at, okay? And we're going to learn how to do it both ways. Sometimes it requires you to graph it. Sometimes you can do it in the calculator and look, okay? So the first thing we're going to do is discuss the steps. What you have to do first is place both equations in y equals mx plus b slope-intercept form, okay, which I have right over here for you. Then you're going to graph each equation separately. So you're going to graph them one at a time. And this is where I always have students get a map pencil so they can graph one in color and then graph one in pencil. Or online, that's real easy to do. Just get 2 colored pens. You're going to place a large point at the point of intersection. Notice we've already said it like 3 times. Write the ordered pair that represents the point of intersection. Yeah. All right. So as a quick reminder of graphing, I just need y'all to remind me for slope. Slope is what over what? It's going to be rise over run, or y over x. Your up and down over your sideways. And the b is where we're always going to begin, okay, on the y-axis. So I just wanted to remind y'all of that really quick. We've done a lot of graphing, so it shouldn't be an issue. So now let's talk about our examples over here. Okay. Example number 1. You have y equals negative 2x plus 1 and y equals x plus 7. So when I look at the first rule, it says that you need to place them both in y equals, and these are both already in y equals. So then I'm going to start graphing. So I'm going to graph this one first, and I'm going to code it in blue so that I know that I'm graphing this one first. And my m is negative 2, which means Kyle's going to go down 2 and over 1. And I'm going to begin, my b value is 0, 1 on the y-axis. So that's this axis right here. I'm going to start my b. And then I'm going to graph by going down 2 over 1. Now, you need to be accurate and take your time with this. And you need to graph the whole thing because we don't know where they're going to cross at. And until you know where they're going to cross, you need to make sure you're as accurate as possible on your line. So the first one you always have to graph all the way across. Then I'm going to take my line and, oops, I don't know why it did it there. Okay. Going to draw my line as accurately as possible because again I don't know where they're going to cross, so that's one of those things that I have to be really careful about. It's way easier to do it in pencil on paper. Okay, so then let's go graph our next one. I'm going to do in a different color, and I'm going to use green, and my m is 1, so my m equals 1, which is up 1 over 1. Remember, slope is always in front of x. And my b value is going to be a 7, so that's going to be 0, 7. Okay, so I'm going to go up here to 0, 7. And I know if I go up 1 over 1, I'm not going to hit that other line. So I'm going to go down 1 over 1. And there is my point of intersection. So I'm going to stop graphing right there. And you're welcome to stop graphing once you hit that point. And there are your 2 lines. Our point of intersection is right here. Okay, and that would be negative 2 comma 5. Negative 2 comma 5. And this is called an independent solution, which means there's only one. This is an independent, all by itself solution over there. Now, let's go do our next one. Okay, I got to put them both in y equals. I noticed the first one right here is already in y equals, but the second one is not. So I'm going to go ahead and do that first just to get it out of the way. So I have 3y. What do I need to get by itself? The y. I need to get rid of that 2x by subtracting. I cannot put the 12 and the 2x together because they do not have the same last name. When the 3 and the y are right next to each other, they're multiplying. To get rid of multiply, you divide. And I split it over here just for ease sake to remind myself to do negative 12 divided by 3, which is negative 4. So now let's pull out our information. Our m is negative 2 over 3, which means Kyle goes down 2 and over 3. And I'm going to start at negative 4 on the y-axis, which is our straight up and down axis. So I'm going to start at negative 3. Sorry, the lines didn't print right in here. Oh, whoops, I mean negative 4. Monday after a break, guys. So I'm going to start at negative 4. And from there, I'm going to go down 2 over 3. And it doesn't matter which line you graph first. I'm just graphing this one because I just solved it. So I'm going to go 2 over 3, up 2 over 3. Oop, this one's going to be tough because clearly it's kind of messing up. And I'm going to draw my line. Remember, you have to do that first line as accurately as possible because we don't know where they are going to intersect at. So we need to make it as neat as possible to make sure that they intersect correctly. Then I'm going to go graph my other one. And for my other one, I will do orange. And I'm going to go on ahead and circle it so I kind of know my color coding and where I'm getting each thing from. So my m is going to equal 3, which means Kyle goes up 3 and over 1 because every whole number is over a 1. And he's going to start at 0, 7. So I'm going to start at 7. And I know if I go up 3 over 1, clearly I'm not going to hit that other line. And there is my point of intersection. So I'm going to go one extra point past that to give myself a nice, pretty accurate line. And graph it. Now, I'm not going to have you guys graph a whole lot because it can be kind of cumbersome. And a lot of times you're just going to have to identify it. So you have to know physically what your graphs are going to be and identify them. But you won't necessarily have to do it by hand is the deal. So just be really cognizant of that. And my solution to this one is this point right here, which is negative 3 comma negative 2. And it is independent. It is one solution. All right. Now we're going to take out our handy dandy calculator and discover how to do it on the calculator. This is all part of your notes. And I have done a couple of extra little things up here to kind of pre-fill in to make it a little bit easier on us. And I will take out my calculator in just a second and display it for you as well. First thing you need to know is they both must be in y equals mx plus b in order to use y equals on the calculator. So that's what we're going to use is y equals on the calculator. So when I look at A, I notice they're both already in y equals, so I'm ready to go to the calculator. Here are your calculator instructions right here, okay? You're going to go to y equals, and you're going to enter both equations. So I'm going to bring that up. I'm going to clear my calculator because I don't know what the last thing was done on it. I'm going to go to y equals, and I'm going to enter both equations. 2/3 x minus 2. And it doesn't matter which one you put where. And then y equals negative, make sure you use the negative key, plus 3. Then the next set of instructions tell us to zoom 6 and make sure that you, this is a big key right here, make sure you, see, the intersection. If not, you have to zoom out. So that's really, really important. In order for it to trace the intersection, you have to actually see the intersection on the screen. So I'm going to hit graph right here. Hit zoom 6. That's your standard window. And I see where it intersects right there. So I'm good. So I'm going to do the next steps. The next steps are to second trace, 5. And then it says this is the first line, first curve. You hit enter for yes. This is the second line you want to trace, enter for yes. And you want it to guess the intersection point? Well, yeah, because usually the calculator can do a little bit better job than I can. So you hit enter 3 times and you get your intersection point of 3, 0. Of 3, 0. And that would be your point of intersection. I'll make that a little smaller so I can have it up on the screen while we're doing it. So you write down your point of intersection, 3, 0. And that's it. That's how you do it in the calculator. So now we're going to go look at our next one. And the first thing we have to do on the next one is put the second problem into y equals. It is a little bit of extra work, but the calculator does the bulk of it for us. So that's not too bad. So if I want negative 3y by itself, I need to get rid of the 2x. I can't put the 12 and the 2x together because they don't have the same last name. When the negative 3 and the y are right next to each other, they're multiplying. So to get rid of multiply, you divide. And I'm left with that becomes a positive 2/3 x minus 4. So now I have my 2 equations that I'm going to put into the calculator right here. So those are my 2 equations I'm going to put in the calculator. So here's my calculator again. I'm going to try and leave those steps up for you. It's kind of hard to get them all on there. Okay? Yeah, I'm not going to be able to. So what are we going to do? I'd rather you be able to see the problem is we're going to go to y equals. We're going to clear both of these because I want to make sure that I type over everything. And we're going to type in the equation. So we have negative 4x plus 5. And it doesn't matter which one you put in first or which one you put in second. And this one is 2 divided by 3x minus 4. In all honesty, you don't even have to simplify. You could just leave it in the form before and type it in. So then we're going to hit zoom 6, and we have to make sure we see the point of intersection. Do we see it on our screen? Yes, we do. If not, you would have to zoom out by hitting zoom and the out button. But luckily, we do see it. So then you're going to hit second trace because we want it to calculate number 5, the intersection point. Then you hit enter, 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 and it tells us that our intersection point is a big ugly decimal. But that's okay because I didn't tell you it had to be in a fraction form, so you can do your answer as you received it or as you got it, and that's fine. So our answer is 1.93, negative 2.71. So that would be our answer to this equation right here. So that's how you do it in the calculator. And then we're going to go down here and we have a couple of special cases. And as you guys can see, I've actually worked out the problems for you on these. You don't actually have to do the problems. Okay, but I wanted to show you what these 2 problems would look like and what your answers would be. So on these, as you can see on the A example, is that they're parallel. So these are actually parallel lines, okay? And they will never intersect. Hopefully they will never intersect. That's the whole point. You don't want train tracks to intersect. And these are considered no solution because they will never intersect. They will never intersect. And like on the other one, it was called an independent solution. This one is called inconsistent. It's an inconsistent solution. We have seen that come up before. Okay. Then when you look at this one over here, you'll notice that it is 2 lines that end up being the same. You've got an orange one or a skinny one if you printed it, and then a green one, okay, which is a little bit thicker. So these end up both being the same line, which means no matter what, they're going to cross on every single point, which means they're going to have infinite many solutions because you will never be able to. Every point is an infinite amount. The line goes on forever, which means any single point that's on those lines is going to satisfy both equations.